In this part of the lecture, we will learn what's the problem of overfitting, and to illustrate this problem that many models may suffer. To illustrate this, I'm gonna use Monte Carlo simulation from the previous lecture. So the plan is that we will play again a role of data god. We will know what's the true data generating process. We will generate some data knowing this true process, and then we will see how different models behave in terms of fitness to those data points. And as we will see very soon, the true models are not necessarily the ones that are the best according to standard statistics. So in the very beginning, it may sound very surprising and very counterintuitive, but you will see that actually this concept is very easy, and I think that it's a very good it's a very good starting point for a discussion about choosing the correct model, and how we should use machines, computers, to help us to choose the best model. So that's the plan for this part. So let's conduct only one simulation, and I will use this seed, and suppose that our true data generating process is given by that y depends on, we create how many observations? Let's say 20, not so many. So let's see how this the problem of overfitness occurs in small samples, and let's create here those 20 observations from normal distribution. And now suppose that we have quadratic relationship between x and y. So let's say that we have this relationship that we want to, that x depends on, that y depends on x, with this parabolic relationship, but in addition to this, we have some uncertainty, for every observation. And so what we would really like to, we have some, if we type this relationship, we have some points. The true data process here is that if we type this way, let's say sec from minus 0.5 to 0.5 to even 2, 2, length out 100. Those are our i's, with our y's, and here we plot against x. Color is equal to orange. So here I plotted this, instead of plotting against x, I use this sequence vector from -2 to 2, because here we have this range, and here we see that this is our relationship that we would like to recover from data points that we observe, and we observe those data points. There is discrepancy between this deterministic relationship and deterministic relationship and realized points because of this component, uncertainty. Yeah, and on average, this component is equal to 0. Yeah, but from time to time, yeah, it's higher, and in other times it's lower. Yeah, so on average it's 0. Yeah, but it generates some noise. Yeah, in our identification procedure. Yeah, so this is it. Yeah, and now we will consider several models, and we will see which models are better and which models are worse to recover this relationship. In our consideration, let's consider 4 models. Yeah, so let's consider linear model, quadratic model, which, yeah, as you see here, this is the true model. But also let's consider more complex models with polynomials of degree 5 and 10. Yeah, so let's first estimate the model, linear model. This is linear model, and yep. So here we see that this intercept is negative, but it's not significant here because on one hand, yeah, here it's increasing for negative numbers, decreasing for positive, yeah, and actually using a linear model, it's hard to capture. It's not possible to capture this relationship. Yeah, so even though that this estimated slope is negative, yeah, it's not significant. Yeah, if we want to plot on the existing plot our model, prediction of our model, we can use AB line. Yeah, so we used this before, but but we provided either parameters for horizontal line or vertical, or also we played around with options A and B, which accounted for intercept and slope. But if we provide, and if our model is linear, and if we provide this fitted model, R is smart enough to extract intercept and slope. Yeah, that are estimated in this model. Let's use color red. You see, this is our model. Yeah, our linear model. Yeah, and yeah, we see that this model is not perfect, undoubtedly. Another model that we want to consider is model square. And we want to introduce x and x square. Yeah, I just reminding you that if we use any nonlinear transformation, we have to use I. Yeah, and this is it. So do you remember? We are data gods. So we know that our intercept next to square term should be something around minus 3, while the estimate for what? For linear term x and intercept should be somewhere around 0. Yeah, so let's check whether this is true. It's close to minus 3, and yeah, if we check, yeah, so those numbers are not 0. Yeah, but we see that both intercept and linear term are statistically insignificant. Yeah, so this is our quadratic model. Yeah, we saved this model, and next we will consider two models with polynomial of degree 5 and 10. Now let's compute the model with polynomial for x of degree 5. Let's create model 5. Yeah, and here first we will do it manually, and it's not the recommended way, because for higher orders it may be a bit cumbersome. Yeah, so we have model 5, we have 5 coefficients, 6 parameters estimated, because here we have intercept. And what I would say what is more recommended is to use function poly. And this function poly, if we provide degree, and what is important, if we want to compute standard polynomials, not some special orthogonal polynomials that I don't want to discuss in this course. If we want to compute something like this, for here it's only for example 1 from 1 to 10, just to see that here we have the first column is our x, the second column is polynomial of degree 2. So for 1 it's 1, for 2 is 4, for 3 is 9, and so on. And we have here polynomials of degree 3, 4, and 5. Yeah, so instead of using this, it's enough that model 5, if we write something like this, poly x 5 row equal to true. And now let's combine. Let's compare coef of this, coefficients of this, and this. You see, they are exactly the same. Yep. So now, instead of writing polynomial of degree 10, let's use this poly 10. Yeah, actually in one of exams in previous years, I asked students to compute the relationship between y and x and polynomial of degree 27 or something like this, and seriously, too many students, they wrote it manually, and they wasted a bit of time unnecessarily. Yeah, so remember to use polynomial of this function poly, because it may be useful someday. Yeah, and this is it. Yeah, here we have coefficient for polynomial of degree 10. Now we will compare goodness of fitness for estimated models. In this exercise, we will use one of the very popular measure for fitness, mean square error, that you can find down there. Yeah, and this measure is nothing else than average residual. Average of squared residual. Yeah, and this is it. And the lower this value is, then our model fits the data better. Yeah, and so let's compare. for our all four models, yeah, and yeah. So we create MSE train, and here now there is small spoiler alert, because this measure, we will compute this measure on the data set that we used to estimate those models. Yeah, and those such data sets are named training sets. Yeah, that we train models with those data sets. Yeah, so MSE train is equal to 4. Yeah, it's vector with 4 elements. Yeah, and the first element is, we take residuals of model linear. This returns residuals, but we are interested in mean of squared residuals. So something like this. Yeah. The second model, the second MSE, is with square. Sorry, MSE train. What's wrong? Okay. I think that was. Yep, now it works. Yeah, I forgot to load this. Yep, and here we have, it should be 5, and last but not least, 10. Yep. And remember, what was the true model from which, yeah, we are data gods. We created those data points, and we know that this true deterministic relationship between x and y is a parabol, yeah, of this form. Yeah, but if we look at this here, I can plot this, plot against 1, 2, 5, and 10. Yep. Okay, it's not visible. Yeah, but we see that. Let's skip the first element, and if we plot this once again, this is because here those differences, the measure of fitness for a linear model was so bad, yeah, that all those remaining 3 models are very similar. Yeah, but if we skip this point by skipping the first element, yeah, and yeah, also I didn't include 1 here, we have something like this. We see that the model which is the best according to this measure, which is very standard in the traditional literature, we will see that the best model according to, if in this horse race of models, the model with polynomial of degree 10 is the best one with the smallest mean square error. Yeah, but that being said, yeah, it's on one hand, yeah, it's not what we would like to obtain, but also it's not very surprising, yeah, because notice that those models, for instance, model with polynomial of degree 5, it nests also the true model. Yeah, so here we have some additional parameters that we can use to reduce our to improve our fitness. Yeah, but in the next part, that I'm not sure whether I record tonight or tomorrow. Yeah, but in the next in the next cut of this part, yeah, I will show that actually this model maybe not this model with polynomials of degree 10 maybe not the best, yeah, and it's, yeah, you know that we expect that this model should be the best, yeah, but yeah, we will see how this will be. In our previous exercise, we found that the lowest MSE, mean squared error, was for the model with polynomial of degree 10 as explanatory variables. Yeah, and now let's use estimated models, and let's plot implied relationship from those 4 different models. Yeah, so we know that the true data generating process, yeah, again, we are data gods, yeah, we created those data points, and we know how those data points were generated. And now for a moment we closed our eyes, we estimated different models, we were fully, and now we are fully agnostic about which model is the true one, and we try to find which model is the model. Yeah, and if we took MSE criteria computed on data points that were used that were used for train our models, then it seems that the best model would be this with the highest degree of polynomials. Yeah, and so now let's plot. So this is before we plotted prediction of linear model for models with higher degree of for higher degree of polynomial higher than 1, we have to do it manually. Yeah, and so now let's plot relationship implied from the square model, and here we will create first sequence of x's from -2 to 2, and for those x's we will make predictions using our models. Yeah, and and here, so we create sequence -2 to 2, length out 100, let's say. So here we have this, and now let's make prediction and for model coef square. Yeah. So here, what we have to do is that we take for each value we will create matrix of intercept 1, our sec, the value of x, and the value of x squared. If we type something like this, we will get the first column is intercept, it doesn't change. The second the second column is x. The third column is squared x. Yeah, and now if we multiply this column by this vector coef model square, yep, we will get for each x we will get prediction of the model. Yeah. Okay. We have y square here. For each x we have implied 1. And now we can plot this lines y square against x sec. Let's use color green or blue, why not blue, and let's use this style that that we want to have dash line. Yeah, so this is LTY equal to 2. You see, we are here with our quadratic model. We are very close to the true data generating process. Yeah. First thing is that why we are different, because we try to imply the true model on some noisy data points. So there is this small discrepancy between this true model and our implied model comes from the fact that our inference procedure is not perfect. Yeah. So we would say that this model is really good, but the problem is that here we know what's the true data generating process. This is our orange line. Yeah. And now let's plot other models, yeah, that we estimated. Let's compute fitted values for remaining models for our vector xsec. Yeah, and if we want to have y5, let's use it this way, and we take poly xsec degree 5. Again, we take it as true, and because of the fact that it still we need intercept, just like here, we have to write something like this: cbind, yeah, and here, yeah, we have colon of for intercept, and x square, x to the power of 3, x to the power of 4, and x to the power of 5. Yeah, and now we take coefficients. Again, I hope that at this moment all of you know that this is sign for matrix multiplication. We had this before, yeah, but just as a reminder, and we take model 5, and this is it. Yeah, so we have those values, and we do exactly the same thing, but for a model with polynomial of degree 10. Yeah, and it should work. Yeah, let's check. Now we are in the position to plot fitted values for a model with regressors being polynomial of degree 5 and 10. Yeah, and here it's enough that we will type y5 against xsec. Let's use color green, and let's use LTY, the style, plotting style, to be 2. Yeah, and the same thing we can do with degree 10, and the color, let's be let's say black. Okay, so here you see that the model with polynomial of degree 5 is a bit, if we zoom those differences, on one hand it's not very far away from the true model, but on the other hand this model is getting closer and closer to realize points that were used to build, to estimate parameters of the model. Yeah, but what happens if we plot the best model according to MSE computed on the training set? Yeah, you see, here this model becomes absurd. Yeah, that I wouldn't believe in this model at all, because yeah, we are quite far from the true model, which is orange one with solid line, and this the more complicated model we consider, then essentially our model become more similar to a child that connects only those dots that she or he sees. Yeah, and here it's essentially that this model is very good in terms of predicting realized values that we observe, but the problem is that this model is not credible at all for other values. For here, yeah, it's far cry from the true model. Here, the predicted value is somewhere here. Yeah, even we don't see this on our plot. Yeah, so now we got to the sort of paradox that the best model, we see that we cannot trust the best model. Yeah, so this is it. Yeah, that it's something that is a really big concern in machine learning. Yeah, that we don't want to have a model that is the best on the considered data set, but in general we would like to have a model which is the best in all observations, even those observations that we don't see. So how to do it? We will talk about this in the next cut a bit, and in the next part a lot. I said that we want to have a model which is not the best in the dataset that we use for estimation, but in general is the best for also for points that were not used in the estimation procedure. In this particular exercise, we are in a super nice situation, because remember, we are data gods. Yeah, we created those data points, and in particular, there is no there are no problems. There is no problem to generate additional data points, some new data points that will be used, that weren't used in the estimation procedure, because yeah, we already estimated our model, but now we can create validation set, new data points from our true data generating process. Validation set. Yeah, and let's create some axis from normal distribution, why not? And we know what's the true relationship between axis and y. We chose this before. This is our true data generating process to the power of 2 plus some noise. Okay, and now we have those. We can plot those points, valid against x valid, and let's use type 3. Yeah, if we, you see, here we have some additional points in the first observation that here we have immediate observation. And we see that, for instance, the best model, this with degree of polynomial 10, which was the best on our training set, here for those points this model is terrible. Yeah, for those points, yeah, all other models are way better than prediction of this. Yeah, and so here we have new data points that allow us to validate those models, yeah, in much fairer way. Yeah, that we will use those points that were not used in this estimation procedure. So now let's compute implied fitted value for our validation points for all 4 models. Yeah, and for in this exercise, yeah, let's create first y1 valid, and we can take here c byte 1 and x valid. Here we have this. And for our linear model, we have only intercept and our variable. Coefficients of this linear model are like this, and here we can do it this way, yeah, and those are our predicted values. Similar thing can be done for squared model, yeah, but here we have to raise also to the power of 2. It should work, yeah. Is it vector? It's safe to check whether the dimensions of output are consistent, yeah. And here we have 100 observation and only 1 column. And why here for y5 valid we can recycle this code, because here we computed fitted values for xsec, and it's enough to only to replace xsec with xvalid, and it should do the trick. Yep. Okay, and last but not least, we replace this with 10 new object, and here it should be 10, and this is 10. Yep, I think so. Okay, so we computed predicted values for our validation points, yeah, and those are predictions, and those are true realizations. So now we are able to compare those predictions with those true numbers. Yeah, so this is what we're gonna do now. Now we will compute those. We will create new numerical vector valid. We have only four models, yeah, and valid one, it will be, we take y valid minus linear valid, we raise to the power of 2, yep, and we take mean of this, yeah, from the MSE formula that we discussed before, yeah, and yeah, this is it. For square model, we have to replace on the predictions, because yeah, those validation points are exactly the same, yeah. And now we take this valid 5 here, and here we create validation for the most complex model, yeah. And now we can see that maybe it's even better to plot this, and we have model of degree 1, degree 2, degree 5, and degree 10. Yeah. You see, before the best model was of degree 10. Here for degree 10, we have some enormous error, because this model was the best on our training set, but on the validation set it did very poor job. Yeah, and now if we compare which, we can type which mean. This will return, this function will return the index for which this MSE was the lowest. And in our case, it's 2. And the second model was the square model, which was the true model, actually. Yeah. So here we see that in our, if we don't, here we were in quite nice situation that we were data gods and we were able to generate some additional points and to validate different models using some external points. But here, and using this approach, we were able to identify the true model, yeah, the one that is not the best for data points that were used for estimation, but also the best which is outside our training sample. Yeah, and I think that this concludes this part of the lecture, and in the next video clip we will discuss how to implement this philosophy in situations when we are not data gods, that we have some scarce data points observed in the real world, and how we can utilize the methods in a similar spirit to identify the model which is as good as possible. Yeah, so that's the plan for the next clip. Yeah, so I hope that you enjoyed this a bit. Yeah, and see you in the next clip. Yeah, ciao.